Welcome back to KU Pulse, the podcast from Khalifa University. I'm your host, Jade Sterling, joined today by Arjen van Vliet, Assistant Professor in the Department of Physics. Welcome.
Thank you very much. I'm excited to be here.
What are we talking about today?
About neutrinos.
Neutrinos. Okay, so you called them originally ghost particles.
Yeah.
Ghost particles from everywhere.
From everywhere, yeah, exactly.
Okay. Tell me more about that.
Okay. Well, neutrinos are very exciting particles. So they're very special particles in that they don't interact with anything. So they can pass through the entire Earth as if the Earth isn't even there. So they're really unique particles in that way, and that's why they're called ghost particles, right? Like as a ghost, they can pass through the wall. So the same goes for neutrinos, and so in fact, a lot of neutrinos are produced in the sun, in the core of the sun. They pass through the entire sun before reaching us at Earth. Pass through the entire Earth as if nothing even is there. So every single second there'll be around 100 billion neutrinos passing through the tip of your finger. So it's very amazing particles, very special particles, and a very exciting topic to work on and try to learn more about.
Well, this raises a whole bunch of questions. To start with, is it only the sun that they're made?
No, they're made in nuclear interactions. So you can have nuclear decay produces neutrinos. So even our nuclear power plants here on Earth produce neutrinos as well. But nuclear fusion inside of any star produces neutrinos. But there are also much more energetic event and exciting events that also produce neutrinos at a completely different energy scale. Neutrinos that are being produced in supernova explosions, for example, and even in more larger scales at, you think, for example, at the center of black holes in center of galaxies, supermassive black holes in the center of galaxies. There, all kinds of processes can happen that produce neutrinos at even higher energies, and there are a lot of different ways and environments where these kind of neutrinos can be produced.
We'll touch on the energy concept in a little bit. What I want to start with is this idea that they're traveling, but they're not interacting with anything. You said, 100 million are going through the tip of my finger at any one moment.
Yeah.
I just don't understand how that's possible.
Yeah, that's the exciting thing about physics, about neutrinos in general. There are a lot of things that are possible which are completely unexpected in daily life, and that they have no connection with our daily experiences, but are happening and are indeed the case. So, and the same goes for neutrinos. They are special particles. They have no charge, meaning there's no electromagnetic interaction happening. So there's no interaction with electrons or electric charge anywhere. They have the only thing that they see is something that's called the weak force. In physics, there are basically four fundamental forces. The gravity. Gravity is incredibly weak if you talk about single particles.
Yeah, I was going to say, gravity is quite strong.
Exactly. But in our world of particle physics, when you look at single particles, gravity hardly plays any role. It's mostly all about electromagnetic interactions, but that only happens between charged particles, and neutrinos don't have a charge. And strong interaction. Strong interaction is what holds the nucleus together. If you have quarks and protons and neutrons together, and you have the strong force holding that together. And then there is the fourth force, which is called the weak force. It's called the weak force for a reason. It's a very weak force. And that's the only force that the neutrino sees, besides a little bit of gravity, because they have a little bit of mass, but that's so small that's completely irrelevant. So really only the weak force plays a role. And that means that it just travels straight through everything, unless it accidentally, with a very, very small chance, happens to interact with the nucleus. And that chance is so small that almost all neutrinos will just pass straight through the Earth without even interacting.
So quickly, neutron, neutrino, two very different things.
Yeah, absolutely.
Okay. Yeah. Okay, good. Just get that one out there, because they're both no charge, but
exactly.
very different things. Okay.
So neutrinos, actually, I think it's Italian for small neutron.
Oh.
So there's neutrons are much heavier, much more massive than neutrino, and very, very different particle.
So let's do this, that they're traveling everywhere. We don't know if they're going to interact with anything. How we're detecting them, we'll get onto that in a moment. But you said they're coming from all sorts of places where there's any kind of nuclear activity. We're talking fission, we're talking fusion, we're talking here on Earth, we're talking supermassive black holes. Can we tell where they came from?
So we can tell from which direction they came in our detections, in our experiments, and that tells you something, give you a bit of an idea.
Okay.
And it depends really on the energy that we're talking about as well. I mean, we can detect the neutrinos that come from the sun if we, with big experiments that looking very carefully at it.
Are they going to have a very specific energy? I don't know what the word would even be, like quota number.
Yeah. No.
So it's a certain
exactly.
range. If you've detected one in a certain range, you can make a reasonable assumption that it's come from the sun.
Yeah.
Whereas if it's more powerful, more energetic, it might have had to come from further away. Is that how that works?
Yeah, roughly. And well, you can see the direction as well where they came from. I mean, you can see that they came from the direction of the sun. If they're
but then they're not going to change direction. It's always
they're not going to change direction. No. And what can change directions in space is, for example, magnetic fields. If you have a charged particle and you have a magnetic field there, then this charged particle gets deflected and a magnetic field and goes somewhere else. But because the neutrino has no charge, it just passes straight on, flies very close to the speed of light, and there's no way to change its direction.
Okay, so you've got a single neutrino, and I think that's the interesting thing, because if they're being made constantly in all sorts of places around the solar system, there must be millions of them. And we're talking about individual ones.
Millions is a very small number.
Yeah. Okay. Right. So what kind of number you want to give it? Like quadrillions?
The total number is unimaginable. I think that's But you always put a 10 to the power and on a very high number. It's
huge, ginormous numbers. Exactly. Okay. And they're still around. They don't disappear. They don't decay. They don't.
No, exactly. Yeah, they're one of the fundamental particles. There are only a few fundamental particles in nature that do not decay, and neutrinos are one of them. So they get produced. They fly around everywhere, and with a very small chance of interacting once they pass through some very dense planet or star or something like that. But besides that, they will just keep on going forever.
Why? What do they do? What are they there for?
It doesn't have to be a reason. It's nature produces them. But yeah, so what in principle, the nice thing that they are necessary in terms of physics for many different kinds of nuclear interactions. So they're necessary to conserve the energy and momentum that is happening in, for example, nuclear fusion interactions, when you fuse two protons together. So without them, that process wouldn't be able to happen, and which means we don't have stars. Yeah, they're created in the process, but they have to be created. If they're not created, that process wouldn't be possible.
Okay. Wow.
So yeah, that means that you need them basically for powering stars, for getting energy of stars, getting heat. Stars are quite important for
just a little bit. Yeah. Okay, so they're tiny. Yeah. They're basically massless, so massless that we don't even consider it when we're looking at them. They don't have a charge. They just come up from outer space, pass through you, you don't notice. Yeah. How on earth are you detecting them? How do you know they're there?
Well, that's a very exciting bit. So because they pass through everything, they're also very hard to detect. But the tiny chance that they do have to interact means that there is some way to detect them. Because if they interact, then you can see the results of that interaction. You will not be able to see the neutrino itself.
Okay.
But after that interaction, the particles that are created after that, those you can detect. But because they are the chance to see them is so small, you need very large detectors to see them, and preferentially with some kind of material in there which has a relatively high density, or at least a way to interact with those neutrinos. And but also a very large volume is important. So that is. For example, where the experiment that I'm part of, that's called KM3net. So KM3 stands for cubic kilometer detector. And so this is roughly the volume of 1 by 1 by 1 kilometer in size. So this is huge. Yeah. This is higher than the Burj Khalifa, or it's incredible in size, and of course a lot wider and longer as well. And this is all just because this chance of interacting is so small that you want to have as large a volume as possible to hopefully get a neutrino that interacts in this very large volume. So so it's all about building the detector as large as possible, and at the same time being very efficient in detecting this one single particle in this huge amount of volume that happens to go through it. So this is very challenging, but really quite amazing that they're able to do this.
It's kind of tripping something for me, because you said there's a countless number of them, so large we can't even consider how big this number is, and you've got a gigantic detector. Yeah. Are you not pinging up constantly? Are you not seeing neutrinos all of the time?
Yeah, well, it depends a lot on the energy range. Okay. The lower in energy you go, the more neutrinos that there are, basically. So, and this Game 3 Net experiment is looking at the highest neutrinos that we have seen in nature. So it actually detected the highest energy neutrino ever observed. And this was published about 1.5 weeks ago now. So there was a very big publication, was on the cover of Nature and all in the press worldwide. So it was a really amazing discovery. So we're looking at incredibly high energy neutrinos. And so the higher in energy, the less neutrinos there are. So they're actually, of those very, very high energy neutrinos, there are very few of them.
Okay.
So, yeah.
So what's special about it being high energy? What does it mean?
Well, it means that it has to be produced in some kind of very extreme environment. Right? You don't, these neutrinos with these incredibly high energies, you cannot produce them in the sun, or you cannot produce them even in a supernova explosion. Even though those are not energetic enough or violent enough to produce neutrinos with this incredible energy. So we know that this neutrino came from space, and we know that it has this amazing energy, and we know the direction from which it came from, but we still don't know where it was actually produced, and that's one of the big open questions now. So what can produce such neutrinos of this amazing energy? It's likely not even in our own galaxy. It probably came from other galaxies, and then there are several different theories, and that's one of the things that we are working on here, for example, trying to look at different models, different theories, and see if those models can explain this kind of neutrino that we have seen.
What's your best guess?
Ooh, that's a very interesting question. I'm personally hoping, and I think it's a good guess to say it's something that's called a cosmogenic neutrino. And cosmogenic neutrino means a neutrino that's been produced by interactions of cosmic rays. Now, cosmic rays are charged particles; they are nuclei. So protons, iron nuclei, anything in between. So we can go through the whole periodic system, basically, and we know that there are cosmic rays out there with incredibly high energies, even higher energy than this neutrino that has been seen. So you need a cosmic ray, but an even higher energy than this neutrino to produce a neutrino. And if you have a low energy cosmic ray, it cannot produce a neutrino with this energy. So you have to have a cosmic ray with an incredibly high energy to be able to produce this neutrino. And that is one way that you can do these incredibly high energy neutrinos. So basically that means that there must be sources out there that accelerate cosmic rays up to incredibly high energies. And those sources, possible candidates, are supermassive black holes in the centers of other galaxies, where, and not even any supermassive black hole. We have a supermassive black hole in our own galaxy, in the center of our own galaxy. But that black hole is not what we call active. And active,
it wouldn't have the energy high enough to create this. So we can't just say, oh, that's come from the center of our home.
No, exactly. Okay. Yeah, and it needs more than just a supermassive black hole. It needs a lot of material around the supermassive black hole as well, and then this material can get accelerated up to very high energies. Once the material is inside the black hole, it will never be able to escape. So it has to be close to the black hole, and there it might be able to get accelerated up to very high energies. And then when that happens, you can already produce neutrinos right there when those cosmic rays get accelerated right there. So that's one option, one possible source, right? This the central area of galaxies to supermassive black holes.
You can understand that this sounds very sci-fi. This sounds very impossible.
Yeah, but that's the amazing thing about physics in general, or especially about astroparticle physics, where you're always talking about things that sounds far-fetched or sounds like science fiction, but we measure it, and it's actually true, and it's actually happening. So that's quite amazing.
You're measuring it. You're saying you have found this neutrino that is the fastest that's ever been recorded. It's shown up on your computer screens. How do you know it's true and wasn't just a random blip?
Okay, so the detector works. I have to say, I wasn't involved with the building of the detector itself, but the job they did on this detector is really amazing. It's a huge detector all the way on the bottom of the Mediterranean Sea. So very dark, very deep underwater. And what they're looking for, they're light sensors, basically. A huge amount of light sensors, tens of thousands of light sensors spread around a very large area. So they're looking for tiny flashes of light at the bottom of the sea. They are very good in timing, for example. So if you see one of the detectors light up for a fraction of a second, okay, yeah, there's no way to know what that was, and there's definitely not a sign of a neutrino. But if you see a large number of detectors, in this case for the neutrino, the highest energy neutrino that was seen, about 30% of the entire detector lit up. So all these different light sensors, tens of thousands of light sensors, all detected a flash of light with a specific timing as well.
Okay.
So you need very specific nanosecond scale timing. And these particles go with the speed of light through your detector. So you have to be very sensitive in the timing as well. And so that means that if the neutrino actually interacted right in the water right before our detector, at least that's what we expect, and then it created something that's called a muon, a charged particle. And this particle also still goes with very close to the speed of light because this neutrino has such an amazing energy, flies and completely through our detector. And when it does that, when a muon flies through water, it sends off light, and this light is then detected by our light sensors. And then we can say, okay, based on the timing and the amount of detectors that lit up, we can tell from which direction this came, and it must have been a neutrino. What is actually also possible is if it comes from straight up into the water, then there are a lot of particles that are produced in our atmosphere that can actually still pass through the water and reach our detector. But this neutrino that came from not from up, but from the side through our detector. That means it must have passed through a very large amount of even rock and water before it reached our detector. And the only particle that can do that is a neutrino.
Again, this just sounds so completely impossible that this thing has gone all the way through the Earth, randomly happened to hit your detector. It's just incredible the odds of that actually happening.
Yeah, but the odds get better because the number of neutrinos is still quite large. It's just very, very hard to actually detect.
Because whatever created that one is going to be creating more as they come. So are they always going to go in the same direction from the same place, or are they kind of when they're generated, are they just pinging off everywhere?
Yeah, so that really depends on the source a little bit. Most of the cases, for example, the neutrinos that are produced in our sun, much lower energy, but they're created in random directions in the core of the sun. So that means that every single direction can send off a neutrino in a different direction. So they're basically starting all in the core, but then going in all directions. But you also have scenarios where, if you now talk about these incredibly high energy neutrinos, then if they are indeed produced at these supermassive black holes, then at these supermassive black holes there are huge jets that are produced. These jets are even larger than the galaxy itself sometimes. So they're really amazing objects. They're shooting out of these black holes in two directions. So then when you have a more a possibility, a possibility that those neutrinos are directed to along the jets instead of that they're in all directions randomly.
So this all sounds really cool, very sci-fi, very amazing. Can we use them for anything, or is it more just knowing that they're there helps us to understand our universe better?
Yeah, so that's the main thing. The amazing thing about their energy is that all that energy is in one single particle, right? Because if you translate the energy that is in that single neutrino to our macroscopic real-world energies, then it's actually not that much. It's comparable to, if I remember correctly, a ping pong ball that you drop from like 2 meters height or so. But the amazing thing is that if you look at the number of particles that are in a ping pong ball, that's a completely different scale. Right? We're talking about macroscopic energies compared with one single subatomic particle, and all that then to the 20-something, 30-something particles that are in a ping pong ball, all of that energy into one of those subatomic particles. That makes it
one single
amazing.
particle that's come from goodness knows where, traveled who knows what different distance, and has passed through whoever knows what on the way to get here and hasn't lost a single bit of energy.
Exactly.
It's just astonishing, really.
Yeah, it is, absolutely. Yeah.
So what's next in this kind of field of research? What are we found them, we know that they exist. What's next?
We found one in this energy range, which is so the big open question really is where it came from and what the source of this neutrino was, and what other sources could be, where we can expect them. And for that, if you've only seen one, it's very hard to say how these neutrinos can be produced and where they can be produced, and what the sources are. So that's really a big open question. And it's not even just the source of neutrinos, because we know that these neutrinos have to be produced by cosmic rays, by charged particles. And So that means that if you found the source of the neutrino, you also found the source of cosmic rays. And the cosmic rays, the source of cosmic rays, have been a big open question in astroparticle physics. No, we don't know that.
Oh.
So this has been, well, since the first discovery of cosmic rays that happened in 1912 or something like that. Since then, the science world, the astroparticle physics world has been looking for the sources of cosmic rays. And again, I'm oversimplifying things a little bit because there's a huge energy range in cosmic rays as well, and then it depends on which energies you're looking at. But this is one of the biggest open questions in our field. And the nice thing about neutrinos is, right, they just go straight, in a straight line, that's it. So if we manage to detect more of these neutrinos and see from which direction they came from, and maybe there is something in that direction which can produce these neutrinos, and if we figure that out, we have solved this age-long question of the sources of these ultra-high energy cosmic rays. So it's really quite exciting for us, at least, for astroparticle physicists.
No, that all sounds really exciting, and thank you so much for being here and sharing all of that knowledge with us, especially the news that it's come out of a project that KU is involved in. I imagine there's going to be lots more coming out of that. So thank you for taking the time, and we look forward to seeing what else comes out.
Me too. Thank you. You're welcome.